Assalamualaikum. So I Salia Kaleem, along with my fellows Anusha Batul, Shiza Wasim and Waza Bahram, are going to present to you some information that we gathered regarding the topic you can see here, the determination of macronutrients and micronutrients by titrations. So here is what we're going to cover, and our main topics are determination of calcium in different samples, then determination of both calcium and magnesium, and then determination of magnesium only, and finally determination of nitrogens. So first we have determination of calcium in different samples, and for this we shall be performing complexometric titrations. So first of all, what are complexometric titrations? These are the diametric analysis in which formation of a complex takes place. Okay, so here is a general method for a solution containing calcium and magnesium. For these kind of titrations, we also add some masking agents like potassium hydroxide pellets and our conical flask that contains our sample solution. These look like these small white beads. You can see here. These pellets dissolve and the hydroxyl ions make bonds with magnesium ions to form a solid magnesium hydroxide precipitate. In this way, magnesium ions do not react with EDTA and only calcium concentration is determined. This sample solution is usually titrated with EDTA, which is ethylene diamine tetraacetic acid, and it has property of chelating the metals and minerals. And the indicators usually used are ammonium perporate, which is commonly known as peroxide, and beta-ether indicator. Well, there is a long range of indicators that can be used along a wide range of pH. The endpoint is just easily determined by observing the color change. Beta-ether indicator usually changes color from red to blue or violet, and peroxide, as you can see here, changes its color from red to lavender or purple. Now, what kind of calculations are generally performed? The number of moles of EDTA required to complexity Ca2 positive ions can give us the number of moles of Ca2 positive, because we already know that the stoichiometric ratio of Ca2 positive and EDTA is 1:1. So number of moles of EDTA can be found by multiplying the molarity of standard EDTA solution with volume of EDTA in liters. Used for titration, this is usually the average value of 3 observations. And weight of Ca2 positive ions can be found by product of number of moles and molecular weight. And then dividing this value with total sample weight and multiplying with 100 gives us the percentage. So the complete formula for amount of calcium in this sample is given as molarity of EDTA into volume of EDTA multiplied by 40.78, that is the molecular weight, and it is then multiplied with 100 and divided by sample weight. The first application is determining calcium content of eggs and eggshells, or studying calcium content during the embryonic development. Calcium is the major inorganic constituent in eggs and embryos. The eggshells are first separated into shell, yolks, albumin, and embryos, etc. And for the eggshells, the inner membranes are first removed, and the shell is first dried in the oven and then cooled in desiccator and read on the analytical balance. It's then dissolved in 50% HCl, and the solution is then filtered, which is transferred to another flask. It is then diluted and pH is adjusted to almost 10 with the help of a buffer. This solution can now be titrated against EDTA, and erythroin black tea or EBT can be used as indicator. The second application is determining the calcium content of liquid and powdered milk, and the procedure is totally same. And the third sample is calcium lactate tablet. These tablets are first ground and finely powdered, and then they are ignited to remove free carbon and then mixed with dilute HCl and water. And the rest of the procedure is same, and EBT can be used as an indicator. Determining calcium for quality control of rosuvastatin calcium present as raw material. Rosuvastatin is used along with a proper diet to help lower bad cholesterol and fats and to raise the good cholesterol in the blood. Thus, it is immensely important for a healthy body. It is usually given in the form of calcium salt, and thus direct titration can be performed, and for this the titrate solution can be magnesium EDTA complex. The question here arises, why are we using magnesium EDTA complex? This is because EDTA in its pure form is covalent and thus insoluble in water or less soluble in water, whereas in its ionic form as this one it easily dissociates into ions, and also in the rest of titrations it is taken in ionic form like complex of sodium ions with EDTA, and upon interaction with calcium ions this weaker complex is broken and new calcium EDTA complex is formed. Hydroxynaphthol blue can be used as indicator, and at the endpoint it changes its color from pink to blue, as you can see in this graph. It really helps for any indicator. In this you can see that when it is not complexed with metal ion, i.e. uncomplexed, it is least absorbing the blue wavelength, which means it will appear blue, whereas in its complex form it least absorbs the red wavelength of visible spectrum, which means it will appear red. Number 5 are liming agents. The most common material used for liming soils is brown limestone. These range from pure calcium carbonate to mixtures of calcium carbonate and calcium magnesium carbonate, which are dolomite limestones. For this, standard EDTA is used as titrant, and QH is used to maintain alkaline pH, and then magnetic stir is used to keep solution homogenized. Calcium indicator can be used and titration is performed till all the green color has vanished and changed into pink. Calcium content can be determined by redox titrations, and redox titrations are the titrations in which there is oxidation and reduction taking place simultaneously. The sample is first ashed, and the ash is then dissolved in HCl to precipitate calcium as calcium oxalate. Precipitate of calcium oxalate are then filtered out and washed, and after washing, these are dissolved in sulfuric acid. The liberated oxalic acid is then titrated with potassium permanganate solution, and this is the reason it can also be called as permagnetometry. And there is no need of using an external indicator because CAMLA4 itself is a self-indicator due to its DD transition, and endpoint is usually indicated by change of color to purple or light pink. Okay, so here is the reaction that occurs. In this reaction, Mn here in CAMLA4 is present in +7 oxidation state, and its oxidation state changes to +2. So it is reduced by gaining electrons, and carbon dioxide in oxalic acid has an oxidation state of +3, and it changes to +4 in carbon dioxide by losing 1 electron. So it is oxidized. Now the question here arises, what is the role of sulfuric acid here? Sulfuric acid is added to prevent the hydrolysis and also to provide the surplus H-positive ions to keep the reaction going. Furthermore, it also helps to maintain the acidic pH, as oxalic acid is a weak acid and is not able to provide the required acidic medium.
This is Anusha Batul. One of my group members, Soliha, has talked about the determination of calcium in the sample. But what happens if we have calcium and magnesium both in the sample and we want to find out both? For that, let's see the process and the calculation followed. Examine the calculation of the determination of calcium and magnesium in the sample by milk titration. Sample can be milk, water or something else, but before studying the application of the sample, let's see what will be the process followed. First step is the standardization of EDTA. Second step is the back titration until first endpoint, and the third step is the back titration until second endpoint. For the purpose of standardization of the EDTA, what we will do, we will add an appropriate amount of the potassium hydroxide in the flask that contain EDTA solution for the purpose of increasing the pH. Then we will add an indicator. Let's say we will add calcium indicators. Then after that, for adding the indicator, the solution will turn pink. Then we will add calcium chloride into the solution until the color changes. The here calcium chloride is the titrant, and we will note the volume of the calcium chloride used and find out the molarity of EDTA and the molarity of calcium chloride. First step, that was standardization of EDTA. The next step is the determination of total amount of calcium in magnesium in the sample until first endpoint. So for this purpose, we will add standardized EDTA calcium indicator to the sample solution. The sample solution should turn pink. At this point, all the calcium and magnesium are bound to the EDTA with some excess EDTA and the indicator in the solution. And when we back titrate it with the excess calcium chloride, then additional calcium from the titrant, that is calcium chloride, will bond with the excess EDTA. As calcium is stronger than magnesium, calcium compete with the magnesium and form bond with EDTA. It results in free magnesium, to which calcium indicator will bind and green color of the sample will appear. This indicates our first endpoint, which means that additional EDTA bond to the calcium. At this point, stop titration and record the volume of calcium chloride used. Next step is how much magnesium in the sample. To the solution after the first endpoint, we will add potassium hydroxide in order to increase the pH. As at higher pH, magnesium EDTA complex will dissociate and precipitate out as magnesium hydroxide. The calcium indicator is free and our solution will turn into pink color. We call the free indicator, or that is calcium indicator. Now we will again back titrate with the excess calcium chloride. The calcium from the calcium chloride will bond with the calcium indicator and again our solution will turn green. This will be our second endpoint and we will stop titration here and record the readings. In order to find out the amount of the calcium and magnesium in the sample, first of all we will calculate total amount of calcium and magnesium in the sample. That was our second step of the standardization. The formula for this purpose is as follows, that is milliequivalent calcium plus magnesium per liter is equal to the milliliter of the EDTA equivalent into normality of EDTA into 1000 divided by milliliter of the milk titrated. After that, we will calculate the amount of the magnesium in the sample by this formula, that is milliequivalent of magnesium per liter is equal to the milliliter of the EDTA into normality of the EDTA into 1000 divided by milliliter of the milk titrated. After the calculation of magnesium in the sample and total amount of the calcium and magnesium in the sample, now to calculate amount of the calcium is very simple. We can easily find out the amount of the calcium in the sample by subtracting the amount of the magnesium in the sample with that of total amount of the calcium and magnesium in the sample. And the formula for this purpose is as follow, that is milli equivalent calcium per liter is equal to milli equivalent of the total amount of the calcium and magnesium per liter minus of the milli equivalent magnesium per liter. First application in the determination of calcium and magnesium is in the dairy products. Complexometer titration is a well-known method with EDTA that is used for measuring calcium and magnesium in powder milk or the liquid milk or any other dairy products. Second application is demineralization of chitin isolation from shrimp shells. Chitin contained in the shrimp shell waste is about 20 to 50% dry weight. Chitin and chitosanes are widely used in skin and hair care products because of the film forming ability, which makes them a good carrier in cosmetics and fixed ingredient on skin for long lasting effects. It is also because of its excellent hydrating agent, which moisturizes and protects skin from drying. Chitin was isolated from the crustacean shells by deprotonation in alkaline solution followed by demineralization in acid solution. Calcium carbonate is the main composition of minerals contained in the shrimp shell, wherein the calcium concentration can be able to determine by complexometric method or titration. Is determination of calcium and magnesium in the soil solution. Soil solution is the medium in which surface and the solution reaction occur. This aqueous solution contains dissolved matter from the soil chemical and biochemical processes, and from the exchange with the hydrosphere and biosphere, this can be occur. Complexometric titration is used for the determination of calcium and magnesium in the soil solution, which are available for take-up by plant. For this purpose, soil sample are fractionated, dried, and then soil solution is extracted by acetic acid, after knowing the properties like pH and cation exchange capacities. These can be titrated by back titration with EDTA, and magnesium ion can be masked by either potassium hydroxide or the sodium hydroxide by the formation of solid hydroxides. Our next application is analysis of the calcium and magnesium in hard water by complexometric titration. Hardness in the water is due to the presence of dissolved salts of the calcium and magnesium that is unfit for drinking, bathing, washing, and is also form scales in the boiler. The estimation of the hardness in the water is based on the complexometric titration. The EDTA is insoluble in the water. The disodium salt of the EDTA is taken for this experiment. Endpoint of is the indication of the blue color. Type of hardness. Temporary hardness and the permanent hardness. Temporary hardness is also called as the carbonate hardness. It is because the hardness refers to the calcium and magnesium carbonates and bicarbonates in the water. Heating the water or reacting it with the lime removes the temporary hardness. Second is the permanent hardness that cannot easily removed by boiling, and it is because of the presence of the chlorides and the sulfates of the calcium and magnesium. The filtrate that contain the permanent hardness producing substances is estimated against EDTA using EBT indicator. Water hardness is usually determined by EDTA, that is a complexing or gelating agent which is used to capture the metal ions. This causes the water to become softened, but the metal ions are not removed from the water. EDTA simply binds the metal ions to it very tightly. Total hardness. Total hardness of the water is estimated by titrating the water sample against EDTA using etiochrome black tea indicator, which has blue color. For this purpose, EBT, that is etiochrome black tea indicator, is added in the solution sample containing calcium and magnesium. It results in the formation of unstable complex of EBT with that of calcium and magnesium. We will titrate the unstable complex in the color wine red with EDTA solution. It results in the formation of stable complex with a pH of 9 to 10, and EBT remained free in the solution, which gives the solution a stale blue color, which will our endpoint.
Assalamu alaikum, this is Raza Wasim, and I'll carry forward the discussion of calcium and magnesium determination in few more products. First of all, the first product is blood plasma. We are doing this with complexometric titration, obviously. There are certain steps to be followed. The first step is the addition of excess Na2-EDTA to a neutral or slightly acidic solution which contains calcium, magnesium, and phosphate ions. Now the question arises why we added Na2-EDTA to neutral or slightly acidic solution. There are basically two reasons for it. The first one is that in an acidic or slightly acidic or neutral medium, there is chelation of calcium and magnesium with part of Na2-EDTA. Chelation is basically formation of multiple coordination bonds between ions and molecules with metal ions. The next advantage is that it prevents precipitation of calcium and magnesium as Ca3PO42 calcium phosphate in the alkaline medium. If it is added in alkaline medium, it causes precipitation. So addition to neutral or slightly acidic solution, it prevents precipitation. So the next step is back titration of excess Na2-EDTA with standard magnesium chloride solution. First of all, we need to know what is back titration. Back titration is a process in which we determine the concentration of analyte by titrating it with an excess reagent, which in this case is Na2-EDTA. The pH maintained is 10 and we use etiochrome black tea indicator. The amount of Na2-EDTA related with sum of calcium and magnesium ions can be calculated, and this is how the etiochrome black tea indicator looks like, and this is its structure. On the other hand, adjusting another portion of the same solution to pH 12 after addition of excess Na2-EDTA releases magnesium from its complex with Na2-EDTA. Precipitation of magnesium takes place in alkaline medium either as magnesium hydroxide or magnesium phosphate. From the back titration of the excess Na2-EDTA with standard calcium chloride solution, we can calculate the amount of Na2-EDTA reacted with calcium using calcine indicator, which is shown here. The next step is the determination of Na2-EDTA magnesium, which can be determined by subtracting the sum of Na2-EDTA calcium and sum of Na2-EDTA calcium magnesium. In this way, the next application is determination of calcium and magnesium in urine. The first step is definitely the collection of urine. 24 or urine specimens are collected in jars containing about 10 ml of concentrated hydrochloric acid. Now the question arises why we need hydrochloric acid. Hydrochloric acid definitely provides an acidic medium, but that acidic medium is required to avoid the formation of insoluble salts of calcium and magnesium during the collection period. So the next step is precipitation of calcium. Manufacturers recommend acidifying the urine before measurement to ensure calcium solubility. There are various steps involved in this process. The first is we take distilled water and mixed urine, 2 drops of methyl red indicator, 1 ml of 4% ammonium oxalate solution to prevent the interference of phosphates in the urine. This is transferred into a conical centrifuge tube. From there, the pH is adjusted by adding 1 N ammonium hydroxide by drops until the color changes to yellow. Then this color actually does not interfere with that of the murixide indicator which will be used. Then we add 1 N of hydrochloric acid until a pink color reappears. Then we mix it thoroughly and allow the mixture to stand for at least 1 hour. Then the centrifuge at about So the next steps are titration of magnesium and calcium, simple titration processes. For titration of magnesium, we decant the clear supernatant into our column and covert. We add 3 ml of ammoniacal buffer, 0.20 areochrom black tea indicator, which I have already shown. We titrate magnesium using alkaline EDTA. We have to remember that phosphate has no interfering effect on titration. For titration of calcium, we take 3 ml aliquot into column and covert. We use 0.4 and NaOH and 0.25 ml murixide indicator. We titrate calcium again using EDTA solution. We titrate immediately after addition of NaOH to prevent reprecipitation of calcium oxalate. Now comes the calculation parts. For calcium, we use the formula U into 10 by S, and for magnesium we use U into 8.22 divided by S. Now what are these terms U and S in this formula? Basically, U is the ml of EDTA which is used in the titration of urinary calcium or magnesium. The same experiment we have performed, we have studied just right now. And S is the ml of EDTA used in the titration of corresponding standard. Next is determination of magnesium. We have discussed calcium, magnesium. Now we'll discuss magnesium. So our first application is determination of magnesium in fertilizers through complexometric titration. Magnesium sulfate is titrated with disodium EDTA in the presence of mordant black 2 indicator, which is basically areochrom black T indicator, which we have already discussed and seen the structure of. This is the same one, until blue color is obtained. So this is how this reaction works. Magnesium, which is the analyte, it reacts with the indicator, which is blue, and magnesium being colorless. When these two react, they form a metal ion indicator complex, which is wine red. The pH maintained is 10. Now this metal ion indicator complex, it is titrated with excess EDTA, which is colorless. This wine red metal ion indicator complex, on being titrated with EDTA, forms metal ion EDTA complex, which is again colorless. Our next application is determination of magnesium oxide and fly ash blended cement through complexometric titration, which involves a series of steps, and we'll discuss the steps in detail. The first one is heating the cement sample with hydrochloric acid for 10 minutes. Then we need to make the solution dilute, and we make the solution dilute by adding 2.5 ml of 5% ammonium oxalate solution, that is boiled. Now, in order to make the solution alkaline, we add ammonium hydroxide, which forms a suspension. That suspension is cooled and filtered. That filtrate is then titrated with standard 0.002 molar EDTA, and fly ash content and percentage of magnesium can be calculated. So our next application is quantification of magnesium content in natural rubber latex by complexometric titration. The chemicals required are EDTA, disodium salt, and areochrom black tea indicator. A conventional approach involves magnesium analysis in RL based on complexometric titration with EDTA using areochrom black tea as an indicator. So dissociation of EDTA disodium salt and EBT, which is the areochrom black tea indicator, depends on the pH of the medium. So addition of ammonium chloride or ammonium hydroxide buffer solution is required in order to control the pH of the solution to be less than 10, which facilitates a reaction between the indicator, and magnesium. At the end point of the reaction, the solution, it changes color from red to blue. That's all from my side.
This is Faiza Behram. I'm going to discuss a method for determination of nitrogen. Now, steps involved in the Jaldel's analysis. The first step is digestion or destruction process. For this step, our sample of the nitrogen, original organic sample, is destructed using sulfuric acid. So the sample is reacted with sulfuric acid in the presence of sample is reacted with sulfuric acid in the presence of copper sulfate, and potassium sulfate is also added as a boiling point increasing agent. Copper sulfate is used as a catalyst. Now in this process, all the nitrogen gets converted to ammonium sulfate. So the reaction goes as nitrogen sample plus sulfuric acid in the presence of copper sulfate plus potassium sulfate gives to ammonium sulfate, water, carbon dioxide, and other byproducts. After this, the next step is distillation step. In distillation step, now the products of the digestion is reacted with the base like NaOH. Now after this step, all the nitrogen gets converted to the ammonia NH3. Reaction goes as ammonium sulfate plus sodium hydroxide gives to ammonia plus sodium sulfate plus water, and nitrogen ammonia that is produced in the distillation step now undergoes condensation. After the condensation of ammonia, the next step is titration step. Titration step, the ammonia solution is titrated using a suitable acid, and the amount of acid that is used for the titration gives us the amount of the nitrogen that was present in the sample. Suitable indicator for this titration process is Tashiro's indicator. Tashiro's indicator is an indicator that indicates the pH value from 4.4 to 6.2 and is basically used in the Jaldel's analysis. Now, this indicator is composed of a mixture of methylene blue and methyl red solution and it is prepared in ethanol or methanol. I'm going to show you the operators for Jaldel's analysis. This is the operators that is used for the general analysis. First, there is a flask that is used for the digestion process. Sulfuric acid is reacted with the sample in the presence of copper sulfate and the potassium sulfate. After this, there is another flask that is in which NaOH is added in the products of the digestion step. After addition of NaOH, NH3 is produced that is passed to the condenser, and after condensation, it is collected in a flask. And then titration of this or NH3 solution is carried out by using a standard acid. Now there is a short video for indication of whole Jaldal process. So first we weigh our samples for digestion process for samples of copper sulfate, ammonium sulfate, and some of or sample of our original nitrogen sample. And destruction process is carried out. For destruction, copper sulfate, potassium sulfate, and the origin sample of nitrogen, they are added in a flask that is called Jaldal's flask. After their addition, digestion is carried out. It takes from almost 1 to 2 hours. 420 degrees centigrade is the ideal temperature, and ammonium sulfate is produced as a result. Color of the solution changes during the whole process. Now, after digestion process, our next step is distillation process. Here digestion completes, and now we'll move on to distillation process. For distillation process, first we weigh out our original sodium hydroxide that will be added to the product that will be added to the solution that was produced after the destruction process. Distillation is carried out, and the ammonia that is produced during the distillation that is added to the flask, and now condensation is carried out. After condensation, next or final step is titration process. Of our titration, a suitable volume or known volume of suitable acid is added to the products of distillation process. Titration is carried out, and the amount of acid that is used, it gives us the moles of the nitrogen that was present in our sample. Applications of Jalal analysis. This method can be used for determination of nitrogen in caffeine and saccharin in pharmaceutical products. It can also be used for determination of nitrogen in proteins, in fertilizers, in sludge and sediments. I'm going to discuss some limitations of Jalal analysis. It cannot be used for determination of nitrogen in organic compounds that contain nitro group, azo groups, or compounds in which nitrogen is present in ring structure. For example, in pyridine, nitrobenzene, and azobenzene. This is because in these compounds, nitrogen in the sample does not get converted to ammonium sulfate, so further analysis cannot be carried out. This was all from our side. Thank you.